Hey there, amazing people. It's so good to see you all again right here on The Art of Rendering. Missed me? Because I surely missed you. Guess what? Today, we are embarking on an epic adventure, diving straight into the mystic waters of producing ultra-realistic images. Ever heard of super resolution? Well, if not, strap in, because we are about to go on a roller coaster ride through the groundbreaking papers. And for all you code wizards out there, stay with me till the end. We've got a Pytorch code walkthrough. All right, team of the art of rendering, let the magic begin. Ever heard of DLSS, aka Deep Learning Supersampling? It's NVIDIA's answer to real-time super resolution. In video games, DLSS operates on a similar principle. It takes a low-resolution game frame and uses AI to upscale it, resulting in crisp, definition visuals that would usually require beastly hardware to achieve smoothly. Think of it as a real-time artist perfecting each frame. And for our rendering enthusiasts out there, grasping super resolution means unlocking techniques to elevate visuals even without proprietary tech, like DLSS. It's a game changer for everyone passionate about crafting stunning digital visuals. Now, let's dive deeper into super resolution on today's groundbreaking paper, straight from the archive, titled Photorealistic Single Image Super Resolution Using a Generative Adversarial Network, a collaborative masterpiece led by Christian Liedig and Lucas, among others. Let's unpack its genius, shall we? The introduction starts with defining what super resolution is. Traditionally, many super resolution techniques could upsample images, but there is a notable missing piece: the intricate texture details that bring an image to life. Most methods simply didn't capture these nuances. The most common yardsticks were mean square error and peak signal-to-noise ratio. While these metrics might sound technical, they essentially measure the pixel accuracy of the upscaled image compared to a high-resolution original. Now, let's check out the mean square error. Imagine you have two images, the original and the upscaled version. As you can see, the highlighted pixel represents the difference between the two. MSE, in simple terms, calculates the average of these square differences across the entire image. The lower the MSE, the closer our scaled images are to the original, at least mathematically. Moving on to PSNR, which stands for peak signal-to-noise ratio. Think of it as a measure of how much noise or unwanted distortion is present in our upscaled image. But here's the catch. While MSE and PSNR give us numerical insights, they don't always align with what our eyes perceive as image quality. An image can have great MSE and PSNR values and still not look right to us. That's where techniques like SRGAN aim to bridge the gap. This paper addresses that problem, and that's where the game changes with SRGAN, which challenges this norm, aiming for an image quality that feels real and aligns more with human perception. In the images above, you will notice the PSNR and SSIM values for each method. The bicubic method and the deep residual network, which is SRSNet, are optimized for MSE. This means they aim to minimize the difference between the original and the upscaled image. Mathematically, on the other hand, SRGAN is a bit special. It's optimized for something we call perceptual loss. Rather than just looking at the math, SRGAN tries to upscale images in a way that looks best to our human eye. So, while the numbers might be different, the real test is how the image feels to us. We will delve deeper into that in just a moment. Now, let's move to the method. When working with super resolution, the goal is simple. Take a low-resolution image denoted by ILR and transform it into a high-definition, super-resolved image labeled ISR. Yet the ultimate measure of success lies in how close ISR comes to its original high-resolution twin, IHR. It's worth noting that we only get to see IHR during training, making it a bit of a bench secret. Our primary tool for this task is a generator function G, a powerful part of the GAN architecture. Its mission is to produce ISR. With every iteration, G gets refined using a trivial loss function, DLSR, which focuses on perceptual similarities rather than just pixel differences. Now, let's move to the adversarial neural network part of our GAN setup. There is a generator G and a discriminator D. In a game of wits, the mission is to produce super-resolved images labeled ISR. These ISR images, when crafted perfectly, should closely resemble the original high-resolution counterparts, IHR. Remember, IHR is only available during training. As G gets better at generating images, D becomes more adaptable at distinguishing between real high-resolution images and those G has crafted. This dynamic challenges G to continually refine its output, ensuring that the resulting ISR image clearly mirrors natural photos. Peeling back the layers, our generator is a deeply structured network constructed with several residual blocks. It's built on the foundation of convolutional layers paired with batch normalization and parametric ReLU activations. To enhance the image resolution, they employed a sub-pixel convolution layer. On the other hand, our discriminator employs a systematic architecture. It houses multiple convolutional layers, drawing inspiration from VGG Network's design. As D works through its layers, it leverages strided convolutions to adjust image resolution. With a rich array of feature maps at its disposal, it concludes its operation with a dense layer, assigning a probability score to its judgment. Okay, now let's move to the perceptual loss function. The perceptual loss function is made up of two losses. First is the content loss, and then the adversarial loss. In the content loss, a popular way to measure the quality of image super-resolution is using the pixel-wise mean-squared error loss. It's simple. Just compute the difference between each pixel in our super-resolved image and the original high-resolution counterpart. This method is favored by many top-tier techniques. However, there is a catch. While this approach yields high PSNR scores, it often misses out on the finer details of the images, leading to visuals that look unnaturally smooth and lacking in texture, something not exactly appreciated by the human eye. So some researchers thought, why not aim for something that resonates more with human perception? Building on pioneering works by Gates and others, this research turns to the VGG loss. This isn't just any other loss, it's derived from the deep features of a pre-filtered VGG19 network, a renowned deep learning model. Instead of just looking at pixel differences, we measure how different the deep feature representations are between the super-resolved and the original high-resolution images. In essence, with the VGG loss, we are not merely comparing pixels, we are comparing perceptual quality and essence. Let's move to the adversarial loss. Beyond the content-focused approach, they have integrated a touch of adversarial gameplay into the generator as it crafts a high-definition image, constantly being challenged by a discriminator. Picture this. The generator, as it crafts a high-definition image, is constantly being challenged by a discriminator, a network trained to differentiate between real and super-resolved images. This pushes the generator to craft images so convincing that even the discriminator can't tell them apart from the real ones. Our adversarial loss is rooted in the probability that our reconstructed image is seen as a genuine high-resolution picture. But here's a twist. Instead of maximizing the odds of the discriminator being fooled, we flip the script. We minimize the negative logarithm of those odds. To put it simply, it makes the learning gradient more consistent and our model more robust. In layman's terms, it's like coaching a team not just to score, but to be so good that the opposing team's coach can't even spot a weak link. Now, let's move on to the enhanced version of SRGAN, which is literally called ESRGAN, Enhanced Super Resolution Generative Adversarial Network. So, let's first discuss the network's architecture. Transitioning from SRGAN to ESRGAN, one of the pivotal changes lies in the architecture. ESRGAN employs a more advanced design known as a residual dense block, RRDB. For its generator, instead of the standard residual blocks used in SRGAN, SRGAN's RRDB comprises multiple dense connections. Additionally, the batch normalization layers present in SRGAN are entirely omitted in SRGAN. This allows the network to learn a broader range of features and maintain the richness of information. Now, let's move on to the next part, the relativistic discriminator. SRGAN introduces a significant twist to the adversarial game, a relativistic discriminator. While traditional GAN discriminators aim to categorize images as real or fake, the relativistic discriminator in ESRGAN evaluates how much more real one image looks in comparison to another. This subtle shift makes the adversarial process more dynamic and robust, encouraging the generator to produce outputs that are not just convincing on their own, but superior when compared to other generated images. Now, let's move on to the perceptual loss. The loss function plays a decisive role in the evolution of super-resolution models. While SRGAN combines content and adversarial losses, SRGAN takes it a step further by enhancing the perceptual aspect. ESRGAN's perceptual loss leverages the features from intermediate layers of a pre-trained VGG network. Now, let's move on to network interpolation. A unique feature of ESRGAN is the concept of network interpolation. It refers to the blending of weights of two trained models. In the context of ESRGAN, the models in question are typically ESRGAN trained with perceptual loss and ESRGAN trained with mean square error loss. By interpolating their weights, the resulting model manages the strengths of both, producing super-resolved images that strike a balance between perceptual quality and pixel accuracy. Now, let's check the Pytorch code for SRGAN. This person did an awesome implementation of SRGAN in Pytorch. Let's check out the code now. Enough of the theory, shall we? Now, let's move on to the datasets class. This data loader serves as an essential component in training deep learning models. It allows easy data fetching with data augmentation that includes flipping an image, which can help improve the model's generalization. First, we retrieve the corresponding image file name with an index. Then, we load the high-resolution and low-resolution versions of the image. Using the PIL library, we convert them to RGB format. With a 50% probability, the images are vertically flipped using the vFlipTorch function, and with another 50% probability using HFlip. Then, the images are converted from PIL image format to Pytorch tensors. Using the totensor function, our dictionary images are returned with both low-resolution and high-resolution tensors. Here, we are using the basic Torch data loader. Next up, let's get into the core of SRGAN, starting with the trainer class. So, the trainer class is where the magic happens. This is where we set up our generator and discriminator. The trainer class takes a bunch of configurations through a config file and sets up the stage for training. First things first, we figure out whether to run our code on the CPU or GPU. The GPU can help us get results faster. We pull in essential settings like the number of epochs, batch size, and image size from the config. Depending on whether we are focusing on perceptual quality or not, we pick different learning rates and loss factors. One fascinating piece here is the relativistic discriminator. It doesn't just say if an image is real or fake. It compares a real image to a fake one and tries to determine which one looks more real. This helps make the model more robust and results more stunning. Now, let's get down to the actual thing. We have two loops. One goes through the epochs and the other goes through our data. Inside these loops, the generator and the discriminator engage in a sort of dance-off, each trying to outdo the other. In our generator, we have three types of losses. Adversarial loss, which tries to make the generated image indistinguishable from the real ones to the discriminator. Then the content loss ensures the important features of the images are preserved. The last one is perceptual loss, which cares about the overall quality of the image, making it pleasing to the human eye. On the discriminator side, the focus is mainly on the adversarial loss. Here too, we are doing something smart by making this loss relativistic, so the discriminator evaluates images in relation to each other. Before we forget, we also adjust the learning rates as we go. The multi-step LR scheduler helps us do that, making our training more effective. As the training progresses, we save our models so that if you need to pause and come back, you can resume right where you left off, thanks to the load model function. That sums up our training class. Okay, folks, we have discussed the code and learned about SRGAN, and now it's time for something super exciting. We are going to compare some real-world applications of super-resolution technology. First, let's talk about VSR, Video Super Resolution. We have two versions of the Hogwarts Legacy gameplay streams. One is the low-quality version at 360 pixels, and the other one has been enhanced using NVIDIA's VSR technology. What's fascinating is that even though the original footage was at a low resolution of around 360 pixels, the upscaled version using VSR looks much better if you take a closer look. So, whether you are a streamer or a viewer, this tech can make a world of difference in your gaming experience. Now let's move to the realm of CyberPunk. We will compare gameplay with DLSS turned on and off. DLSS, Deep Learning Super Sampling, is NVIDIA's proprietary upscaling tech. Rolling the clips, watch how the game transforms with DLSS on. Look at the lighting, the sharpness, and the minute details. Not only do we get a visual treat, but the game performs smoother as well. As you're watching this comparison, keep an eye on the intricate details and the performance. The difference might not jump out initially, but once you see them, you will appreciate the power of these technologies. Technologies like DLSS offer impressive gains not just in quality, but in performance too. Whether you are streaming or gaming, these features could make your game experience a whole lot better. And there you have it. Folks, NVIDIA's VSR and DLSS technologies go beyond the hype. They truly deliver on their promise. So, the next time you are streaming or firing up CyberPunk, remember you have some nifty options to make everything look and run better. All right, folks, we've delved deep into the world of super resolution and even had a chance to see NVIDIA's VSR and DLSS in action. Whether you are into math, gaming, physics, or graphics, there's something here for everyone. If you found this video insightful and want to catch more content like this, go ahead and hit the like button. Don't forget to subscribe to stay up to date with all the exciting stuff we will be covering. Thanks for tuning in, and I'll see you in the next video. Adios.